Hello everyone. So the topic we have for today is examining computer memory and executing instructions. So the objective that we have is to learn how to enter programs into memory and trace their execution. So today we are going to have a look at a program called debug that allows us to view memory and to enter programs into the memory as well as trace their execution. So one thing to note is that we will be working in the real address mode or in virtual 8086 mode of the processor, and we will be using the 16-bit registers. So using the debug program. So the debug program is used for testing and debugging executable programs. And a feature of debug programs is that it always displays all the program code and the data in hexadecimal format. And any data that we enter into the memory must also be in hexadecimal format. The debug also provides us with a single step mode, which allows us to execute a program one instruction at a time, so that we can view the effect of each instruction on the different memory locations and the registers as they change. So here in front of us we have some commonly used debug commands. Let's go through each one of them. The first command we have is the A, which is for assembling the symbolic instructions into the machine code. So in this, using this command, we can put some assembly language code in the memory, and it will convert automatically to the machine code. Then we have the D, it's for displaying the contents of an area in memory. And as we like said previously, it will be in the hexadecimal format. Then we have E for entering data into the memory. Along with that, we have to specify the location also, at what location we have to enter this data. Then we have the G command. It is for running the executable program in the memory. So just to remember, you can remember like G is for go. Then we have H for performing hexadecimal arithmetic. We have N for naming the program. P for proceeding or executing a set of related instructions. So P is like we will be not like stepping one by one, but it will be like to execute a certain uh, subroutine or the set of commands that we have in line. Then we have the Q to quit the debug session, R to display the contents of the registers in hexadecimal format, T for tracing the execution one instruction at a time. So if we want to go instruction by instruction, we will use the T command. Then we have the U for unassembling the machine code into symbolic code. Also, there are a few rules that we need to keep in mind when working with the debug program. That debug program does not distinguish between lowercase and uppercase letters. So we can enter the commands in any case we like. Then debug assumes that all numbers are in hexadecimal format. So spaces are used in commands only to separate parameters. And the segments and offsets are specified with a colon in the form segment colon offset. So you'll be having a better understanding of all these commands that we have used and the rules that we have seen once we start using this debug program. So let's go back to the machine that we have set up last time to start working on it. So we are in the uh, software section. Let's go to the DOS and use the tab key to change the location of the pointer, and we'll try to start with the commands. So now that we are in DOS, let's start the debug program. Again, we can use smaller case, uppercase, it shouldn't make a difference. If we just see the same thing I will do with the caps lock on, it should do the same thing. Okay, so let's try to see some memory using this command. So to do this, we can use the D for displaying the contents of an area of a memory, as we had seen in the previous slide, and we need to give it the location that we have to see. So DS is for the data segment and the location is 200, just any random location. So as you can see on the screen that we are seeing the we are displaying the contents of the memory. So there are three different columns that we have here. So this column, first one, is for the address from which we are viewing the memory. The second is the hexadecimal representation of the data that is there in these addresses. And this third column is the ASCII representation of this hexadecimal data. So if you see here, we have 8 bytes in one side and there is a small dash in between, and 8 bytes on the other side. So each byte can contain 2 hexadecimal characters. So this one line is displaying 16 bytes of memory, out of which each byte is containing 2 hexadecimal characters. Also, the D command, it can be also used to list the contents of the registers and the status of the flags register. So first and we can use Q to quit the program. So the first exercise that we have is we will examine the BIOS data area. So in this exercise we will be looking at the contents of the BIOS data area in the low memory beginning at location 400H, or to describe it in segment offset, it will be 40 and the 0th offset. So BIOS initializes the values in this area when the computer is turned on and updates them during the program execution. So let's try to see the first 16 bytes of the BIOS data area containing the addresses of serial and parallel ports. So again, this above command ds data segment and 200, we can enter it in 3 different types. Like even if we do just like something like this, it should work absolutely fine. And even if we change the case, like it should be working fine. Okay, all right. So the first 16 bytes of the BIOS data area, let's try to have a look at it. .40 and the 0th offset. So F803, this is the first 8 bytes, first 16 bytes of this BIOS data area. So this is actually showing us information about the serial and parallel ports of our computer. We can also check system equipment. For that, an equipment status word in BIOS data area provides primitive indication of the installed devices. So this we can locate at the location 410 and 411. So already we can see it here, but let's try to look at it using this command. We have 40, 10, okay. So here we can see we have the value 25 and 52. So let's try to convert this 2552 into the binary format. So as you know already, so this is in the reversed byte order. So once it is loaded into memory, it will be like 52, 25. Okay. So let's try to convert it. As you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 digits. Okay. So let's try to have a breakdown of this. Okay. So I'll type these numbers out on this notepad here. We have 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1. Great. So as you can see here, these are this is the binary number that we got, and this is the byte position of the bits. So this is the 0th bit, first, second, third, fourth, likewise. Okay. So in this number, the different positions will tell us some different information about the system equipment. So for example, let's try to understand the number of serial ports attached. So for this, it is the bits 11 to 9. So we have 11 to 9. It is 001. So 001 to binary. Let's try to check what it is. So it is 1. So there is only one serial port. Then we can check the number of diskette devices that we have. For this, the bits are the 7 and 6. So let's have a look, 7 and 6. So it is 0. So we have 0 diskette drives like in the machine right now. Then we have initial video mode, which is represented by the bits number 5 and 4. So 5 and 4 is 1 0. So 1 0 is for 80x25 color. So it is a color display of the resolution 80x25. And yeah, similarly, other equipment also we can observe by using this data. Okay. So using this also we can check the keyboard shift status. Okay. And this information is stored on the memory location of 17, 40, 17. 40 is the segment and 17 is the offset. Again, we can see it here, but still, let's type it out. As you can see, it is 60. So let's try to turn off the caps lock key and see the memory location again. As you can see, now it is changed to 20. So similarly, looking at the different locations, we can get information about the keys, the status of the different flags that are set, the information about the computer equipment. Okay. Also, now we will try to examine the ROM BIOS of the computer, and let's try to have a look at the copyright notice and the serial number information of the computer. The computer's copyright notice is embedded into ROM BIOS at location FE000. And to view this segment, we will be keying in the command D FE00 and the offset as 0. So as you can see, this is the copyright information and it is more observable here in ASCII format. You can see the IBM 1991, 1981. So this is the copyright information that starts at this location. Also, we want to see what is the next contents. We can just keep on pressing D. It will show the next memory locations and whatever information it contains. Something like this. So we will now try to check the ROM BIOS date. The date that the ROM BIOS was manufactured, and it is recorded as month, day and year format, and it is stored at the location quad F5. So let's try to have a look at it. D 4 times F and the offset location as 5. So if you see here, we can see the ASCII representation as 62591 and 6th is the June, 25th June 1991. So this is the manufacturing date of our ROM BIOS. So now that we have viewed all the information, we can quit this program using the Q. Okay. So we had a look at examining BIOS data area. We had a look at how we can examine the ROM BIOS. And now we will be looking at executing program instructions. So there are two types in which we can program the instructions. One is the machine language, another is the assembly language. So we'll be actually using assembly language and skipping the machine language for now. Okay, coming back to our program. So let's start it. To enter the program in assembly language, as we had seen in the slides, we can use the A command, and then we need to specify the memory location. We can either specify it as the offset segment offset format or directly in the offset. So before we do that, I'll just show you the status of the registers, all of them. So if you see here, we have the AX, BX, CX, DX all are 0, and these are the pointers, space pointers, source index, destination index, data segment, extra segment, stack segment, and we have the code segment, instruction pointer. Okay, these are all pointing at the different locations in the memory. So the instruction that we are entering right now, it will be on the 102A 0100. So code segment, we can start the entering the first instruction. Okay. So let's put in a small commands like of few instructions and try to understand what is going on. So first instruction that we have is move into CL. CL is the code segment low register, and let's move the value 42. Okay, we have move DL to A, then we have add CL and DL, and then we have jump instruction back to the starting of the program, jump 100. So once we are done with putting in all the instructions, we can press enter 2 times to notify the program, the debug program, that we are done typing our instructions. So now that we have keyed in our program, uh, now we have exited the like A command as well, that we have finished the instructions to be given. And now we can see here are the different memory locations and the commands that are stored in those memory locations. So as you can see, 102A segment and the offset at 0100, we have the move command, and subsequently we have different commands set 102, 104, 106. And before we actually go ahead and execute the program or these instructions, let's use the U command, the unassemble command that we had seen previously, to examine the machine generated code. So if you see here, pressing the U command, we can see the machine generated code at the different memory locations. So for 1022A 0100, we have B142. Then we have for the next instruction DL2A as the B22A. So this is the machine, this second column here, this one is the machine generated code for the above assembly code. So what we can do now is, like, let's have a look at the state like all the register again and what all things they have. So if we see here, AX, BX, CX, DX all are 0, and the code segment CS is pointing to 102. the memory location, starting memory location, this one, and the instruction pointer IP is at the offset 0100. This is the 0100, and the first instruction that it will execute is the move into CL the value 42. So this is the value, this is the instruction that we had entered on the first line using the assemble command. So to go instruction step by step, we will use the T command. So if you see now, in the first instruction, it has executed successfully. And if we look at the registers, we can see that in the CL, in the CX, it will have CH and CL. So in the CL value, the 42 has been uh, put in successfully. Then we have the DL2A. Now let's execute this instruction, and in DL you can see the 2A has been inserted successfully. Then we have add CL and DL, and they have been successfully added. And then we have jump to 100, so it will again go back to the starting first instruction of our program. So normally what we do is, like, when we add these CLDL values, we also have to initialize some space of where to store the sum of those values. So now let's quit the program, start it again. And now we will be having a look at using the int instruction. So int instruction is the interrupt instruction, and in the following coming up examples, we will see how you can request information about the system. There are different types of int operations, some of which require a function code in the AH register. So AH register, this one in the high part of the AX register, AH. So we will have to put the function code in the AH register, and using that different function codes, we can use int interrupt int instruction to request different information from the system. So during the execution of the int instruction, rather than using the T command for single stepping, we will use the P command, which is, like, you can remind yourself as a proceed command, P, to execute the whole interrupt routine, and then come back to our program for executing the next instructions. So before we do the programming, we just need to make sure that the instruction pointer is pointing to the start of the memory location. If you see here, instruction pointer is 106, so we just need to make sure it is pointing to 0100. To do that, if you see here, instruction pointer is pointing to 0100. Yeah, so that's correct. Okay, so in this first program that we are doing here, we will try to get the current date and time from the system. So to do that, we'll have to go to the assembly part of the program. So we can put some assembly instruction. We will put as move into AH 2A. So as we discussed previously, we have to put the function code into AH. We are putting 2A here, and then we will be giving the interrupt instruction as int along with the function code 2A. So here 2A we have put in. Now the int 21, and then again jump back to the initial location. Okay, now that we have entered, now we can execute the program. So we'll start with the T. Now we are executing. If you see here, the 2A has been initialized in the AH. Then we will put in the P instruction to proceed, because we don't want to step in the instruction, the interrupt routine. So it will complete the routine and come back to the third instruction. So if you see, the routine is completed in 21 and we are now at the JMP 0100 instruction. So if you see here, in this we have some values here that are changed. So for example, in the CX register, it is supposed to store the year that we are in right now, so 0707 E9. Let's try to see what value does it decode to. If you see, it is 2025, so that is correct. Then in the DH, great, in the DH and the DL, it will store the month and the day of the month. So in DH will be the month and DL will be the day of the month. So we have DH as 01. So 01 already we can understand it is 01 is 01. So it will be January. And 1F, let's try to see what is 1F. So 1F, it converts to 31. So 31 is like the 31st of January 2025. So this is one of the functions that we saw using the interrupt instruction int. We can also use this int instruction for displaying contents with a different function code in the AH register. So let's try to do it. Again, we start the debug program. So in this, we will be displaying some data on the screen, and yeah, let's start with the program itself. So we start with the assembly instruction. We put in the command move into AH, the function code 09. Then we have the move instruction into DX, value will be 109. So we are putting the 109 is the location in which maybe we can go 107. 107 is the location that we can put the contents that we want to display on the screen. So that address contents we will store in the 107 location. So as of now, you can see we are putting this instruction in the 102 memory location, and the instruction that we have is that whatever data is there in the 107 memory location, to store it in the DX register. Then we have the int 21 and the JMP 100. So I think it should not have been 107, it should have been 109, because on 109 we were supposed to give the data. So let's try to do it again. Moving to AH09, move to DX107. Off, the mistake again. Great. So now here we can specify the data. So dB is for data byte, and we can put some data here. We will put our channel's name here. And then we should put the dollar sign so that the uh, instruction understands that the data that is to be displayed is over. So it is the like it is like the end of characters. Okay, so we entered 2 times and the program is over. Let's have a look at the registers. So it is pointing to the first instruction correctly. Let's execute it. So first instruction, if you see in the AH09 has been successfully uh, stored. Then we will do the next instruction, move into DX109. As you can see, it has correctly worked. And now for the int instruction, we will be using the P for proceed. And if you see here right now, the contents that we had specified in the DX address 109 have been successfully displayed on the screen here. And again, if we go run this instruction JMP100, it will go back to the first instruction that we had executed. Okay, we'll quit the program now, start it again. Okay, so now we will use the int instruction, the interrupt instruction for keyboard input. And for this, we have the function code as 10. So let's have a look. Start with the assembly instructions, move into AH. The function code we have is 10. Then we have int 16, and then we have JMP 100. So the first instruction, MOV, provides function code 10H that tells interrupt the INT instruction 16H to accept data from the keyboard. The operation delivers the character from the keyboard into the AL register. Okay, let's try to execute it. So now we are in the int instruction. Let's proceed. And as you see, it is now waiting for us to input something. So I will put one character, and the character I have put is R character with like the capital R, and it should have been stored in the AL register. So it is 52 here. So I will try to convert this 52 to the binary and from binary back to decimal to understand how which character we have put in. So decimal comes to 82. So 82 is the decimal, and if you see here 52, it converts into decimal 82. And if we go here in the 82, the ASCII table, it is the capital R. So it is the correct key that has been stored in the register value. Okay. So we quit the program again, start it over. So again, instead of quitting every time, you can just reset the pointers of the registers, or like instruction pointer and the memory location where you are putting in the instructions. So like if we start with the A command, we just have to mention the register, sorry, the memory location address again, something like A100. So yeah, can do that as well. So now we will have a look at a small program in which we will try to use the PTR operator. Okay, so I will put in the program first, and then we will try to understand the each instruction. Okay, we have move AX, address value, so now here you can see okay, so I think we have messed up the memory locations here. So instead of 11A, it should have been 119, because that was the place we were supposed to uh, key in the data bytes. But no worries, we can start over again. Okay. Okay. Great. So yeah, okay, we can still use 11A, shouldn't be a problem. Okay, so move into AX 11A, add AX 11C, Okay, great. So looks like we are done typing our program, and let's try to understand now the each line of the program. Okay, so the first instruction that we have is the move AX. So in this instruction we have, it will move the contents of the memory location AH and 11 11AH and 11BH into AX register. So the square brackets that you see is the location of the memory address, and instead of moving actual value, it will just go to the memory address that we have here 011A. So whatever is kept here in this address, it will be stored in the AX register. Then second we have the add AX instruction. So in this, it will add the contents of the memory location 11C. 11C means, here if we see here, 11C is 11C, H and L, so 0500. So these values will be added to the AX. Then we have add AX25. So in this instruction, it will add the value 25H, the hexadecimal value of 25, into the AX register. Then we have the instruction of move the contents of the AX into this 11E memory location. So 11E, we have just initialized it to 00. So after we complete this instruction, whatever the addition value that is there in the AX, it will be stored in the 11E memory address. Then we have this move instruction, move word PTR, the address and the value. So we have to note the use of word here, word PTR operator, which tells the debug program that the 25 hexadecimal value we have to move into a word memory. So if we don't give this word, the debug program does not understand in uh, what memory it has to store this value. So it can be byte or word, or how much memory is to be allocated to store this particular value. Then we have the byte pointer. So if you see here, we have the value 30, we have to move it into the byte pointer in the 122 memory location. So this time, instead of word, we are using 1 byte memory to store the address. And then we have the jump instruction. So again, it will go back to the starting of the program. After that, we have defined the byte values as 14 and 23. Both of these are hexadecimal values. So this is the DB. It is like, defined bytes. So these are the bytes that we have defined that we can use in the above instructions. And we have defined more bytes here. So again, 05, if you remember, from for above we are using it, and these two are the memory location. We have just initialized them, these byte locations, to store the uh, results of the calculations that we do in the above instructions. Okay, so let's try to execute the program step by step and see how everything goes. So T, okay, we should have seen the first instructions, but now we have executed the T command. That means the first instruction has already been executed. So here we can see the instruction pointer is pointing to 103. So IP is pointing to 103, and first instruction move AX11A has already been successfully executed, and here you can see AX value is 2314, and if you see the value of 11A is the 23. So 23 is the 11. So if you remember, this 14 and 23, they will be interchanged when it is being stored in the register. So whatever is stored in the location 11A 1423 in a reverse order 2314, it has been stored in the AX register. So this one is the correct instruction that has been executed, and the next instruction that it will execute is the instruction pointer is 103 here, and the instruction that is to be executed is the AX. It will add the value of whatever is there in the 11C05 value into the AX register. So let's execute it, and if you see in this AX register, if we add 5 in 14, it will become 2319. So this also has been successfully executed. So similarly, we will run the third instruction again. So third instruction was to add 25 value in the AX register. So if you see, if we add 25 hexadecimal value to the 2319, we get the value as 233E. So this is the hexadecimal value again. And the fourth instruction that we have is to store whatever is there in the AX register in the 11E memory location. So before we do that, let's try to see what is already stored in 11E. So D 11E. So in 11E, if you see right now, it is 00. Okay. So now we will do the next instruction and run the command again D11E, and if you see here, we see here it is stored as 3E23. So again interchange it, and we can see 23 3E from the AX register. The reverse byte are stored here. Okay, so let's complete the next instruction. Next instruction is the move byte pointer. Okay, so 30 value is to be stored in the memory location 0122, in which one byte okay, so this is not the instruction. So this is the instruction word pointer 0120. So 25 is to be stored in this 0120 location by allocating a word memory address, word memory size. Okay, so let's try to look at this memory location 0. So if you see here, 25 has been stored successfully. And along with that, you can see the memory location memory that it has been allocated. So these next two zeros are the part of the same defined word, okay, that we can store a bigger value as well. Then the next instruction we have is the move byte pointer. So the value 30 into the memory location 0122. So let's execute it, and let's try to look at the memory again 122. So if you see here, the 30 has been stored successfully. Okay, so all right, this was all that we had for today. But before we end the video, let's try to understand what are the key points that we covered today. So the first point being the debug program is very useful for testing and debugging the machine language and assembly language programs. So machine language we did not see, but we just saw like the machine language conversion of the assembly code. And this debug program, it has different useful operations like display and entering, and the trace command, the execution of step-by-step instruction. And also we need to keep in mind that the debug program does not distinguish between the uppercase lowercase letters, and we can put the commands in any way where we want. The debug command also, like whatever information that is entered or displayed, all of it is in the hexadecimal format. And if you enter any incorrect value in the data or code segment, we can use E command to correct it. Again, we did not use this, but in the coming videos we will use this command a lot. And also, to use the T command, we can use it for executing single instruction at a time, and we can use the P command to execute right through the interrupt routine. Okay, then to resume the execution to the first instruction, we have every time just specified this JMP 0100 instruction. But if, let's say, you are in the middle of the program and you wish to go to the starting of the program again, all you can do is you can set the instruction pointer to 0100. To do this, what we can do is reset IP, and it will ask you the address. So as of now, if you see here, IP is 00118. Here also you can see 0118. If we just specify the location as 100, and again if you see, IP is 0100 and it is pointing to the first instruction. So to reset the pointer of the instruction pointer, reset the address of the instruction pointer, we can use this R means reset IP, or you can say even register of the instruction pointer to the location, whichever one we specified. Okay, and yeah, so that's all we have for today, and I will see you guys in the next video. Okay, thank you so much for watching and have a nice day.